Hello, welcome to video lectures. Today's topic is on uniform bending. Myself, Karanam AJITH, Assistant Professor, Vijayanagara College, Hosapete. Now let us understand what is uniform bending. Consider a beam which is initially unstressed, which is represented as shown in figure. When the beam is subjected to a constant bending moment, that is zero shearing force, along its length as would be obtained by applying equal couples at each end, the beam will bend to the radius r, which is represented as shown in figure. When the bending is taken place, then the top fibers of the beam, that means the top layers of the beam, will be subjected to a tension and the bottom to a compression. Then it is reasonable to suppose that somewhere between any 2 points at which the stress may be zero, the locus of all such points is known as neutral axis. The radius of curvature is then measured to this axis. If the beam is loaded uniformly on its both the ends, bending of the beam forms an arc of a circle. If the elevation is produced in the beam, then this type of bending is known as uniform bending. In order to compute the value of bending stresses developed in a loaded beam, let us consider a beam AB, which is represented as shown in figure, which is supported symmetrically on two knife edges at the points C and D, and loaded with equal weights mg at each end, which is represented as shown in figure. Then the reaction of these knife edges, which is equal to mg, let P is the mid portion of the beam. Consider the equilibrium position of the beam PA. Then the only external force on this beam or mg acting vertically downwards at the point A and mg acting vertically upwards at the point C. That means you are observing that there are two equal unlike parallel forces not acting along the same straight line at the point A and C, which constitute a couple. These constitute a couple of moment that is given by mg into A, where A is the length of the beam projecting beyond the knife edge. The internal bending moment is given by YA square divided by R. At equilibrium condition, internal bending moment is equal to external bending moment. The internal bending moment is however given by YA square by R. External bending moment is nothing but the moment of the couple given by MGA. Since MGA is a constant, then R is also a constant. Therefore, beam is bent into a form of an arc of a circle of radius R. Then the bending in this case is said to be uniform. If L is the distance between the knife edges and Y is the elevation of the midpoint of the beam above the knife edges. From the property of the circle, we have 2R minus Y into Y is equal to L by 2 into L by 2, which is represented as shown in the figure, that is in the form of a circle. If Y is the small compared to R, then the higher order terms such as y square can be neglected. Now, if you take y inside the bracket on the left hand side, we get the first term is 2RY, second term is minus y square, that is equal to L by 2 into L by 2 is L square divided by 4. Now, here if we ignore the higher order terms such as y square, then 2RY is equal to L square by 4, or y is equal to L square divided by 8y. Then substituting this value of R in the equation of Young's modulus. That means if you refresh ourselves the expression for the Young's modulus y is equal to mga by a square into R. However, this value of R is just now found to be equal to L square by 8y. If you substitute back this value of R in the expression of Young's modulus, we get the expression for Young's modulus to be y is equal to mgal square by 8ya k square. Then for rectangular cross section, if B is the breadth and D is the thickness of the bar, then the area of cross section of the rectangular bar is given by A is equal to BD cube by 3. Then when we substitute in place of capital A, if you substitute BD cube divided by 3, then we get this particular expression of the Young's modulus as y is equal to 3mgl square A divided by 8bd cube into yk square, which happens to be an expression for Young's modulus. I repeat, the expression for Young's modulus y is equal to 3mgal square divided by 8ybd cube into k square, which happens to be an expression for Young's modulus for the rectangular cross section. Thank you.